So, what I'm going to be doing over the next 3 or 4 lectures is look at one of the oldest areas of computer science. So, it's a subject that's called information theory, and it looks at two fundamental questions. What do we mean by information? And how do we measure information content? I like this quote. It's from the American writer and journalist Norman Mailer, and it's in his report of his experiences during the anti Vietnam War protests in the late 1960s. And he says of middle class America, they were brusque to the world of manners. They had built their hope of heaven on the binary system and the computer. One and zero. Yes and no. So, a couple of things I'd like to point out before going on to the main business of this part of the module. The material is not covered in the module textbook. When I was writing, uh, I thought very hard about this, and eventually, for reasons discussed in the book, I felt it wouldn't be possible to include it. It's included here for the sake of interest. Information theory, as I said at the start, is a fundamental, very important area of computer science. Uh, Personally, my feeling is it's something that should at least be introduced in first year. So, what's the background to this subject? Well, when one carrying out some kind of computational activity, very often one will eventually hit a need to send data, text, to someone else. This might be something as simple as just sending a text message on a mobile phone. It might be typing up an email message, all sorts of contexts where that activity is going to arise. So think about sending an email. What happens? Got to compose the email and compose the text in an email by repeatedly selecting keys giving the message content. So you might hit a keypad or a touch screen to select the letter S. And when you do that, that character, that letter, is added and stored. When you have completed and are ready to send a message, it is going to be sent through what is referred to as a channel. Now, a channel may be a specific mobile network frequency, it may be a physical channel, such as an optical cable, or even something like a simple copper wire. When the message arrives, it's processed, the content is discovered, and at the final activity, the content of the message will be displayed in some form on a phone screen, on a display unit, possibly even something like a typewriter. So, where are the problems that arise with this activity? The first problem is you cannot send characters directly. You cannot send a letter A, a letter S, a letter T, because for transmission purposes, all you can use are the digit 0 and the digit 1. So the first problem is that characters have to be encoded in binary. And when you send a message through a channel, how long is it going to take is one issue. What if there's interference, what are referred to as noisy channels? And information theory, this is the field of computer science that studies that type of question. And it offers robust solutions that deal with defining what one means by the content of a message, by the uncertainty of the information. It looks at how fast, the limits on speed and the limits on how much you can compress data by. It asks whether data can be sent reliably when there's background noise or other type of interference. It asks what steps one can take to ensure that data is received properly. So here's a model of communication. One has a source, could be a keyboard, mobile phone, whatever. The text being sent originates there. It is passed through a device called, which produces the encoding. The encoded text is then passed through a channel. When it arrives, it is decoded and then finally shown on the destination. While all of this is going on, it's possibility that there is noise in the background. This could be static effects, it could be something like a washing machine or a vacuum cleaner. So that particular picture is called the Shannon paradigm for communication. There are, rather biased opinion, I think, two important research papers in the area of computer science. Both of these papers are very old. The first one from 1936 is Alan Turing's on computable numbers with an application to D and Schrodinger's problem. Turing's paper effectively asks the question, what is it possible to compute? The other paper is Claude Shannon's A Mathematical Theory of Communication. This appeared in two parts in mid to late 1948. Shannon's paper is the foundation of information theory as a scientific subject. So it formulates the key questions, the key issues. It constructs a supporting framework for studying these issues, and it derives some of the fundamental results. So one of the discoveries in Shannon's work is the connection between information content and what one may loosely describe as uncertainty. What do I mean by that? Quote from Shannon's paper: the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. What Shannon is saying is the fundamental communication problem is sending a message from one point to another point in such a way that the contents of that message can be reasonably accurately determined. So And that's the quote from Shannon's paper that I mentioned on the previous slide. The basic question that Shannon is asking in that paper is, what is information? So I have been through earlier lectures promoting the view that the fundamental computer science question is, how do I count? How do I measure? The angle looked at from Shannon's viewpoint is rather different. For Shannon, the fundamental question in computer science is, what is information? So, oh, what happens when we try to communicate with someone? Doesn't matter whether it's in speech or a text message or in written form. What we work with, the basic units we work with, are words. What's a word? A word is a sequence of symbols from some underlying alphabet of symbols. Communication is the process of sending information, and information is a sequence of symbols. So, in order effectively to communicate, to send a message, the receiver of that message has to be able to recognize individual symbols in the stream that the sender of that message has produced. So we have this sort of model here. We have a source of symbols, and these arrive at a destination. So the receiver sees a stream of symbols. Now, in English and most languages, some symbols are going to occur more frequently than others. And some symbols are going to be fairly rare. So, for example, in English written text, the letters E, the letter T, that occurs quite often. On the other hand, the letter Z, the letter J, they'll be seen less frequently. So, what that means is that if a receiver sees, for example, the letter T, they're not going to be that surprised by it. But if they see the letter Q, which is rarer, they're going to be more surprised. So information contains an element of surprise. We expect to see some things, we do not expect to see other characters. And if one is surprised, one is gaining information. This is one of the key discoveries of Shannon's work. When we are surprised, information is gained. So, an example. If we look at English language text, the letter Q is usually followed by the letter U. So, if a receiver sees the letter Q in an input stream of text, then almost surely the next symbol they will expect to see will be the symbol U. There are very few words in English, relatively, that begin with the letter X. And so, in a similar way, if a symbol for the space character is seen, which is indicating that the next character will be the start of a new word, the receiver is going to be surprised if the symbol seen after the space character is the character X. So, surprise is information gained. Information gained is a reduction in uncertainty. You are more aware of the background, you feel less uncertain about what the content is going to be. So we can think of arbitrary alphabet collects a set of n symbols, S1 through to Sn. And a message is just a sequence of symbols. So that gives rise to two questions. How do we measure the degree of uncertainty in seeing a particular symbol or seeing a stream of symbols? How do we encode symbols using binary so that we have desirable properties? So, for example, that a message can be compressed as much as possible. Oh, messages are sequences of events, and there are some consequences of that. In arbitrary stream of symbols, some we will expect to see very frequently, others be quite rare. So we can think of attaching a probability to each individual symbol. So this probability, p sub I, that is the probability that the next symbol we see in our stream of symbols being sent is the symbol S sub I. So when a receiver does see a character S sub I, they have gained information as a result. And the reason for that is from being in a state where they don't know what the next symbol is going to be, that uncertainty has been reduced. They have seen the next symbol, they have gained information, they are no longer as uncertain, no longer as unsure. So the uncertainty associated with an individual symbol with a particular probability distribution that is defined to be minus the logarithm to the base 2 of the probability of that symbol occurring. Now, we're dealing with a probability, so typically probabilities are going to be less than 1. And as a result of that, the logarithm is going to be a negative value. So the uncertainty measure as minus log to the base 2, the probability, that will be positive. Informally, that measure can be thought of the amount by which the uncertainty is decreased when the symbol is seen. So the information that we have gained from seeing a particular symbol. If we have a rather tedious alphabet, which only contains one symbol, S sub 1, then that can be the only symbol that's ever going to appear. So the probability of seeing it is 1. The uncertainty, minus 1 log to the base 2, 1 is 0. What's that saying? It's saying there is no uncertainty because the only symbol we are ever going to see is S sub 1. And it also means we don't gain any increase in information. If we see anything at all, it is only going to be the one symbol in the alphabet. Major contribution in Shannon's work is what is called the uncertainty formula and how that leads to limits on a problem called source coding. So what's source coding? As I mentioned earlier, we cannot send symbols directly. We cannot send the letter A. We cannot send the letter E. We have to encode characters as binary sequences. And a number of standards for that, which you'll met already, so things such as ASCII, things such as Unicode. These are conventions for representing characters as particular binary sequences. And the source coding problem, as it's called, has three main questions. First of all, is it possible to compress the number of bits needed to encode symbols? So it might seem, if one has a 32 character alphabet, that one has to use on average 5 binary characters to encode symbols. The other question that's coming as a consequence of that is, on average, how many bits do you need to encode symbols? What are good algorithms that maximize the amount of compression one can obtain? If one has a high level of compression, one can send more data in less time. However, if we compress information, the receiver must be able to recover that information. The receiver must be able to decode what has been received. So we have this notion of what is called the uncertainty formula and the source entropy. So we introduced P sub I, this probability, as the probability of seeing a particular character in a stream of characters. There's one assumption that is made, which is that these probabilities in a particular environment are independent. If we see the symbol S sub I at time t, then the probability of seeing another symbol S sub j in the next time step, that doesn't change. It's still P sub j. Now Shannon has a result of major importance. He derives, I stress derives, this is not a definition, what is called the uncertainty in a data source arising from a particular alphabet. What is that? This is the uncertainty formula. So that defines the uncertainty in a alphabet with particular probability distribution. What does one do? One sums up over all of the symbols in the alphabet the uncertainty associated with that symbol. And this is sometimes referred to as the entropy of the symbol source. Very important point about this, the entropy in a source depends on the distribution, what determines the likelihood of individual symbols appearing. It does not depend on the alphabet being used itself. And the source coding theorem, the first major result in Shannon's paper, that states that the average number of bits you need to encode a symbol, that must be at least the entropy of the source. So let's look at an example. Suppose we have a 4-character alphabet, A, B, C, and D, and that each of those characters is equally likely to appear. We calculate the entropy for that setting. We find it is exactly equal to 2. We have 4 times a quarter, the probability of each symbol, times log of a quarter, and we take the negation of that and that gives us minus log to the base 2 of a quarter, which is 2. And so that is stating that we have to use at least 2 bits for some symbol when we are transmitting it. And one thing we could do is use the encoding. We encode A using 2 zeros, B 0 1, C 1 0, and D is 1 1. And if we take a particular setting, suppose we're sending 100 megabits, then that encoding scheme is telling us we are going to need 200 megabits. What if we have a different setup? What if we know that the probability of seeing an A isn't a quarter, it's a half? The probability of seeing a B is a quarter, and the probability of seeing a C or a D is 1 over 8. So we're no longer dealing with an each symbol is equally likely distribution. We're dealing with a distribution which is skewed towards seeing the letters A and B. Well, we could use the same coding scheme, but if we look at the entropy of that particular distribution, what do we see? A is contributing minus a half times log of a half. B is contributing minus a quarter times log of a quarter. And C and D are each contributing minus an eighth log of an eighth. And if we add up what that computation gives us, we discover the entropy of that system is 1.75, 1 3/4. And 1.75 is less than 2. Is it possible to exploit that reduction? Previously, we knew we had to use at least 2 bits on average. Now, with this new distribution, we know we have to use at least 1.75 bits on average. Is it possible to do that? Well, what if we use this coding? We use a single bit for our most frequently occurring character A. We use 2 bits for B, a 0 followed by a 1, and 3 bits for C and D. And if we look at the expected amount of data that we're going to have to transmit, well, we expect to use 50 megabits on sending A's, another 50 megabits on sending B's, and 75 megabits sending C's and D's. So now the position we are in is to send our 100 megabit of data. We don't expect to take 200 megabits. We expect to transmit 175 megabits. So we have an overall saving on the amount of data transmitted. In order for that scheme to be effective, a key point is we have to have good estimates of the relative frequency of different symbols. So we couldn't use a scheme where if A occurred very rarely in a text, it would not be a good idea to give it the shortest possible encoding of a single bit. If we have a large data file, then it is possible to analyze data compression exactly. We can get the relative frequency information by direct computation before transmitting the data. And we assume, of course, that the receiver will be informed of or will know the encoding scheme that we're using. So, important sub-area of computer science is what is called source coding schemes. So the source coding scheme that states that the number of bits we have to use on average is at least the entropy in the source, this gives us a lower bound. And that lower bound is actually optimal. We can achieve it to within very insignificant additive term. In order to do that, in order to see how that's done, it involves a study of something called coding schemes. So what are source coding schemes? We have our alphabet, and we are looking for mechanisms to associate binary sequences with each symbol in the alphabet. So that's called a binary code. It's a set of code words. And for each symbol in the alphabet, we have a distinct code word. The example, one which I'm sure you're familiar with, if we look at the original ASCII code, so that's a particular coding scheme, and that uses 7-bit binary codes for 128 distinct characters. So those are that's the first part of information theory, is the notion of source coding. I am going to move on to, in the next lectures, to the other important area of information theory, which is called channel coding.